Okay, so for part B, the problem is that there is a vertical asymptote at x equals 2, therefore it's going to be continuous on the interval from 1 to 2. So we want to rewrite this as the limit as b approaches 2 from the left, because that's where the asymptote occurs, and then it's going to be the integral from 1 to b of 1 over x minus 2 dx. So we have the limit as b approaches 2 from the left, and when we integrate that, we get natural log of x minus 2 evaluated from 1 to b. So we have limit as b approaches 2 from the left of natural log of b minus 2 minus ln, and that should be 1 minus 2. And basically, if we're approaching as b approaches 2 from the left, that's going to approach negative infinity. So therefore, this diverges. Okay, so when we cannot evaluate an improper integral directly, we want to first determine whether it converges or diverges. If the integral diverges, then we're done. If it converges, then we can use numerical methods to approximate its value. So our next way to determine if a function converges or diverges, we do a comparison test. So if we have a function f of x, which we know is greater than 0, so it's above the x-axis, if it's less than some function g of x for all values, then we know f of x is going to converge if g of x converges. This just means, basically, if the bigger one converges, then the smaller one converges. So f of x, in this case, f of x is the smaller one, and g of x is the bigger one. On the other hand, if g of x diverges, then f of x is going to diverge. So in other words, if the larger one, this time we are comparing f of x and g of x, however, now if the bigger one diverges, then the smaller one is going to diverge. Or actually, I'm sorry, I said that backwards, but because the word if. So if the smaller one diverges, then the bigger one diverges. Okay, so example 4, use the comparison test to determine whether the integral converges or diverges. So we are going to compare basically this function, 1 over x cubed plus 1. This is going to be greater than or equal to 0. And then here, we're going to compare that to 1 over x cubed. And since we know, if we were to do limit as a approaches infinity of 1 to a of x to the negative 3 dx, I'm just looking at the larger one. So that's going to become a to the negative 2 over negative 2, or x to the negative 2 over negative 2. So we have 1 over negative 2a squared minus, and then it's going to become plus 1 over 2. So this is going to go to 0, and so we get a half, so therefore this converges. So since 1 over x cubed converges, which is the bigger one, again, if you add 1 to the denominator, that's going to make that smaller. So therefore, the integral from 1 to infinity of 1 over x cubed plus 1 dx converges. Next one, we have the integral from negative infinity to infinity of dx over the square root of x to the 4th plus 1. So taking a look at this part, so kind of comparing just the largest degree. So we want to compare 1 over the square root of x to the 4th plus 1 is going to be greater than or equal to 0, but it's also less than or equal to 1 over x squared. So if we can show 1 over x squared is going to converge, then we can show that the smaller one is going to converge. Now this one has 2 limits. So over here on the side, we're going to have, so it's going to be the limit as a approaches negative infinity. And then we're going to have the integral from a. I'm going to define that to 1 because 1 over x squared is not defined at 0. Again, this top number is kind of irrelevant. You can pick any real number. So that's going to be x to the negative 2 dx. And then plus the limit as b goes to infinity, the integral from 1 to b of x to the negative 2 dx. So we get limit as a approaches negative infinity of negative 1 over x evaluated from a to 1. And then here we get the same thing, negative 1 over x, but evaluated from 1 to b. So we have negative 1 over 1 minus negative 1 over a, so plus 1 over a, plus limit as b approaches infinity of negative 1 over b minus negative 1, so that'll be plus 1 over 1. And so we can see that we're going to get negative 1 plus 0 plus 0 plus 1, so we get 0. Therefore, 1 over x squared converges. So with all that work, since that's the larger one, this implies that the integral from negative infinity to infinity of 1 over the square root of x to the 4th plus 1 dx also converges. Okay. Find the volume of the solid obtained by revolving the curve y equals x e to the negative x from 0 to infinity about the x-axis. So when we have this curve, we think this is our radius. So our volume is going to be pi, and then the integral from 0 to infinity of x e to the negative x squared dx. So what we're going to need to do is create the limit as a goes to infinity, the integral from 0 to a, and that's going to be x squared e to the negative 2x dx. And in order to integrate that, we're going to have to do either integration by parts or tabular method. I'll do tabular method over here on the side. So this will be 2x, 2, and 0. Now keep in mind, this is going to be e to the negative 2x over negative 2. So it's going to be negative 1/2 e to the negative 2x. Do that again, and we're going to get positive 1/4 e to the negative 2x, and then negative 1/8 e to the negative 2x. And then we draw more arrows. It's going to go plus, minus, plus. So now when we write this, we're going to have our limit, and then we are going to have a negative 1/2 x squared e to the negative 2x, and then minus, and then 2 times a fourth, so that'll be minus 1/2 x e to the negative 2x, and then minus 2 times an eighth, so that'll be minus 1/4 e to the negative 2x, and we want to evaluate this from 0 to a. Okay, this actually can be simplified. So we have limit as a approaches infinity. Now all of these have, if I actually factor out or find a common denominator and move the e to the negative 2x to the denominator, so I'll basically have a negative 2x squared minus a 2x and then minus 1, and this will all be over 4e to the 2x. Just makes it a little easier when I'm evaluating. So now I have basically negative 2a squared minus 2a minus 1 all over 4e to the 2a. And we want to subtract that, so we want to plug in 0. So that's just going to become a negative 1 over 4. And this whole part here, this is, since it's over e, we know exponential functions grow faster, that's going to go to 0. So we have pi times 1 minus negative 1/4, so it's going to be pi over 4.